Okay, so, and then the next part is talking about an application of this idea for changing the velocity because of an acceleration vector. Okay, it's an area of projectile motion. All right, projectile motion is not too bad. It's all about organizing, just like we did in kinematics. Okay, so let's talk about a few of the concepts. So we already mentioned about the changing of velocity. Okay, and I said that as the acceleration vector points downward, we see that that's how the direction of the velocity changes. Then I mentioned something about if the vectors were parallel, that it would change the magnitude, and if they weren't parallel, they only change the direction. So let's talk about that first. So here we have a ball, and it's sent up on a path. Okay, so if we look at each point, there's a velocity vector at each point. So here's the initial launch velocity. Now that velocity breaks up into two vectors. Okay, and we saw how to do that in the vector video. I can break it into a horizontal, and I can break it into a vertical piece. Now, throughout this entire path, we know the only acceleration is gravity. Okay, and it's pointing downward. So because of that, if the acceleration is always downward, that's going to cause the velocity that's vertical to change. Because since those are parallel, those magnitudes will always affect one another. Okay, so for that reason, sometime later, so now the ball is, say, here. The velocity is tangent to the curve, the velocity vector. And if I go to, well, hang on, I drew that too big. All right, so the important thing is, because of the acceleration is only changing the green line, the red line should stay just about the same. Well, it should stay exactly the same. I'm just trying to draw it right. Okay, and then the acceleration is going to cause the green line to decrease a little bit. Now if I try to draw the resulting vector, you'll see that it got a little shorter than the first one, and it's even turning a little bit. As I go to another point, again, gravity is the only thing affecting on it. So if gravity is straight down, then the next velocity should be even smaller. And since we're at the top of the path, this would mean there is no vertical velocity. However, since the downward acceleration does not affect the horizontal motion, we still have the same horizontal velocity to the right. So at every single point, we will have the same horizontal velocity. It doesn't matter where we are in the path. The horizontal velocity does not change. However, the vertical velocity, because of gravity, will start to get a little bigger, a little bigger, and a little bigger. And so at each of these points, the resulting velocity, as you can see, is turning sharper and sharper towards the ground because it's going to speed up as it falls back. Okay, and so that's the main idea of how the projectile motion occurs and why it's changing direction, why its magnitudes and its directions are changing. So what we want to do is analyze a problem for this. So let's say we have an object that, we'll start simple, is sitting on top of a table. We'll say the table is 1 meter tall. The object is rolling straight off the table at a velocity of, we'll say, 3 meters a second. Okay, what we want to know is we want to be able to predict where on the floor this is going to land. For a projectile, this is typically called the range. So our goal is to find out what is the range of this projectile.
So to get started, the important thing to know is that projectile motion is just like it's kinematics. I mean, it's not like it is kinematics. Okay, throughout the entire motion of this object, you have two accelerations. You have a constant vertical acceleration, okay, and then horizontally, nothing is pushing the ball, so you have no acceleration. So horizontally, it's always moving at a constant speed, but vertically, gravity is going to increase or decrease that speed. In this case, increase it. So to solve the problem, we're going to do kinematics the way we've always done. We're going to start by listing all of our variables. So we have the initial position, the final position, initial velocity, final velocity, acceleration, and time. Now, one of the things that's going to be different is we've got two dimensions to work with. So rather than using x's to denote my position, okay, I'm just going to write these as a generic s to say position. Okay, so just a new variable just to label it when we make this list. And the reason why is because now what I want to do is I want to split this list into two columns, horizontal motion and vertical motion. Okay, so as we go through it, we're going to list everything we know about velocities, positions, accelerations, and time for each for each direction. So in this case, horizontally, the initial position of this object is 0, right? It's starting right here on the horizontal axis, which we can call 0, and then the final is the range. Okay, and this is what we're looking for. All right, the initial velocity in the x direction was 3 meters per second. Okay, and since there is no acceleration in the x direction, this velocity is going to stay the same. Okay, for the y direction, it starts at a height, so it starts at 1 meter. It ends on the ground. Now, the initial velocity, since we're launching this horizontally, there was no initial vertical velocity for this projectile. The final speed, we don't know how fast it's going to be going as it impacts the ground. But we do know that the acceleration is due to gravity, so we know that that's 9.8 meters per second squared, and it's downward because it's negative. Now you'll notice when I made this table that the time spot, there's no line dividing it between x and y, and that's because in projectile motion it's important to know that the time to move horizontally is going to be the same time to move vertically. Okay, the time is linked between the two. However much time it has to fall, that's how much time it has to move outward to the range. Okay, so we don't know anything about time. Now, since the goal of this was to find the range, okay, that means we're looking for r. Now, if that's the final position, the only equation I can really use for this, since there's no acceleration, is that the final position is equal to 1/2 acceleration time squared plus the initial speed times t plus the initial position. And since there's no acceleration, we know that the 1/2 at squared term is going to disappear. We also start at the origin. Now, just so you don't have to reinvent this wheel every time, for a projectile, once it's in the air, this is the only equation that we can use to solve for how far away it goes. Since there's no acceleration, this is the only thing that exists for us to use. Okay, so you don't have to keep picking the long kinematic equation to get here. In the end, we should know that that is our limit. So if we're looking for the range, and we know the velocity was 3 meters a second, the only problem is we do not have time. Okay, so before we could do this, we need to get time first. Now, since we've already gone down the x to come up with our equation, and that's what made us realize that we don't have time, now we can look at the y column and try and figure out time from there. Okay, so let's change our perspective and try to figure out what is the time of fall. Okay, so if we look at our list, the only thing we don't have is the final speed. So if we go to our kinematics, the only equation that doesn't have final speed is the 1/2. Oops, sorry, I didn't want the right eye. Y1 is 1/2 at squared plus initial velocity times t plus the initial position. Now keep in mind we're in the y direction this time. So we can go through and simplify some things. We know that vertically the initial velocity was 0, right? We have that listed in our table. The final position is the initial position is 1 meter, but the final position is 0. So what's left is we have 0 is 1/2 at squared plus y initial. So let's put in our numbers. This is 1/2 negative 9.8 times time squared plus the initial position of 1 meter. Okay, and if you solve this for t, you will get a time of roughly 0.45 seconds. So now that we know the time of fall, we can plug that into our equation to find the range. So the range is going to be 3 meters per second times 0.45 seconds, and that'll give us a range of about 1.4 meters. Okay, so if we were to set up this setup in lab, you could have a marble. It's rolling 3 meters per second when it reaches the end of the table. Say the table is 1 meter high from the ground. We could accurately predict that this marble is going to land 1.4 meters from the end of the table. And that's actually the next lab you guys are going to do. Okay, so doing projectiles is fairly easy when it's being launched horizontally. But more realistically, what if it's not being launched horizontally? So in this example, what we're going to do is we're going to say we have, say, a projectile, whatever it is, it's a ball of some kind, and we want to launch it up on top of a table. Okay, so we will say that the table is 5 meters away and that the height of the table is 1 meters. Okay, so if we launch this at, say, we'll say a 50-degree angle, what velocity do we need to launch with? So what is the initial launch velocity? So it's kinematics still, and everything applies just the same as it did before. We're going to make a list. So our velocities, acceleration, and time. Okay, we're going to list out our variables for both x and y directions. So initial in our horizontal position, we'll say it starts at 0 and has to get out to 5 meters. For the y velocity, for the y position, we start at 0 and we end at 1 meter. Now, we don't know the initial launch velocity for either the x or the y. Okay, we know that for the final speed in the x, it's going to be the same, but we don't know what it's going to be in the y. Acceleration we know is 0 in the x, and it's the acceleration due to gravity in the y, which is pointing downward. And we don't know anything about time. So this one's going to require us to do some extra steps just so that we can solve for some variables and make substitutions later. For example, so if we want to start with our x equation, remember with no acceleration, this is the only equation we can work with, we get that 5 meters is equal to Vx times t. Okay, so if I solve this for t, I get 5 meters over Vx. So that's about as far as I can get for time. Now what do I get if I plug that in to the y equation? So we got y1 is 1/2 at squared. This would be initial velocity in the y direction times t plus the initial vertical position. So let's go through this. So the final y value is 1 meter. We know the acceleration is negative 9.8 meters per second squared. We know the time is 5 meters over the x velocity. Okay, the y velocity we know is just, well, it's unknown, excuse me, and the time is 5 meters over the x velocity. And then the initial y position was 0. Okay, so you could see that the algebra is going to get a little messy here, but it's okay. We can work through this. Because you're going to have 1 meter equals negative 4.9 meters per second squared. Okay, this is going to be 25 square meters over the x velocity squared plus Vy over Vx times 5 meters, and then of course with 0. Okay, so what can we do from here? You've noticed we've got two unknowns, but we can make an easy substitution here if we understand the trigonometry of our triangle. This term, Vy over Vx, if we look at the picture, our initial launch velocity is just the hypotenuse to a triangle, where we've got Vx as the adjacent side and Vy as the vertical side. So what do you get if you put the opposite over the adjacent? Okay, it follows that the tangent of that angle, which is 50 degrees, is equal to the opposite over the adjacent. So what we actually have in our equation is 1 meter, so negative 4.9 meters a second squared, 25 square meters over Vx squared, plus the tangent of 50 degrees, oops, not plus, times 5 meters. So now we only have one unknown to solve for. Okay, so let's figure out how we can move this stuff around and solve for Vx. Okay, so I'm going to start with a new slide to do this. So the last equation we had, okay, 1 meter is negative 4.9 meters per second squared times 25 square meters over Vx squared. Plus the tangent of 50 times 5. So we're going to do some basic algebra steps here. So if I start with negative 4.9 times the 25, this gives me negative 122.5 over Vx squared. Okay, and then 5 times the tangent of 50 is going to be, let's see, that's about 5 point, well no, we'll go with 6. It's right around 6. Okay, so we've got a few steps here. So if I subtract the 6 over to the other side, we've got negative 5 meters is equal to negative 122.5 over Vx squared. So now we'll multiply Vx to both sides, Vx squared. Okay, so negative 5 meters times Vx squared is equal to negative 122.5. So now we'll divide off the -5. And let's see, that'll give us 24.5. So that means our x velocity then is, so Vx, 4.9 meters per second. Now, the question was asking for what is the initial velocity? So we've got the x component. So how do we find the overall initial velocity? So remember, the initial velocity is the hypotenuse of a triangle of 50 degrees, and we just found the x piece to be 4.9. So if I'm going to find the hypotenuse then, it follows that the cosine of 50 degrees is equal to the adjacent over the hypotenuse. So then the hypotenuse would be 4.9 over the cosine of 50. So the overall launch velocity has to be 7.6 meters per second.